So this is not my usual thing, but we had some discovery in germanium that I will try to get into. But I think this is kind of part of a bigger synthetic material type effort that comes with different aspects. And actually, thanks, Martin, for giving a lot of topics that I understand and I think is relevant. I don't know exactly how to bring it together yet. So the idea starts, it was 10 years ago that we kind of started thinking whether group 4 can be superconducting. And I don't know if you remember, around 2010 and before, there were lots of kind of doping schemes that made superconductivity group 4 happening in carbon, in diamond, and various things. But then there was really no control over what is the crystal structure, why is it superconducting, and things like that. And we started with that, thinking that what kind of, if you have such a thing, what else can you get out of it? I guess that was kind of the big question. And what we do usually in the lab is a lot of quantum Hall effect, a lot of cavity QED stuff, and basically, this was pioneered by Jerome Feist, to put like a resonator on a quantum Hall, and what is that coupling, and does it make sense to have these lambda levels that are much bigger than the resonator of this? Would they kind of work? And I guess this has been discussed quite a bit. The real challenge was we don't do optical photons, right? But we do microwave photons, and in microwave photons you have a lot of controllability in so many ways, right? You can do this quantum non-demolition measurement. You can get really good efficiencies if you want to. You can control, individual things. And a lot of this effort has been taken toward, I would say, qubit research, superconducting qubit research. And that has resulted in these really big objects, and you really have to scale up to do anything meaningful. And I guess that's kind of a challenge, right? So the question we wanted to have was that, can we make a very controllable defect-like object that can be scaled, but it doesn't have to be necessarily like a qubit. So I will try to show you some of the efforts toward that application. So it was really inspired by, I think, optical lattices that you can basically trap two-level systems of some sort, that they have their energy scales, but this is fully controllable. In condensed matter, usually we don't have these two-level systems. I mean, things are too small in the atomistic level. To create something like this, that you have a two-level system, you can have NV diamond and some other defects, but usually they happen in random places, right? And to kind of combine superconductivity with these kind of individual atoms would be great, because superconductivity is usually a very controlled mechanism, right? We can control a lot of things like the previous slide about it, but we can't really arrange them in such a way, right? And if this object was a Josephson junction that small, then I could have done actually quite a bit. Right? So this turned out into a material science question that, what kind of, I guess, Josephson junctions do I have? And if you go through the literature, categorically, there are two types of Josephson junctions. One is this, I would say, insulating Josephson junction, that basically wave function has to decay between the two leads. The other one is that where you actually have a normal region in the middle that has to carry and rebound states, right? So that's kind of like a wave that kind of is in between here and carries the current. Here is just really like a decay, right? And most aluminum oxide junctions are the core, but it's been used in most Josephson junctions. Over here, we have used indium arsenide for a while now, and we can create Josephson junctions. The problem is the length scale, right? These are beautiful because they are so narrow and small, like a few nanometer. Here you have macroscopic effects, which is great because then you can tune things, but at the same level, so I'm gonna start looking up on the material science problem, and then hopefully come back to the quantum material part. So if you look at aluminum oxide aluminum, that is kind of the textbook of all these junctions. So aluminum is obviously crystalline at the beginning. When you oxidize it, you go to aluminum oxide, which is amorphous, and then you try to put another metal on top, right? So this interface is already destroyed here, and then maybe something comes back, right? So if I look at it from the material perspective, I have a perfect material, and then I kind of put something amorphous on top, right? I mean, it is amorphous. I have defects. I have all sort of things that could come, cause trouble, like, two-level system that basically absorb if you are doing a single photon operation. My other luck is that there is some sort of a two crystalline materials, but then the lattices don't match quite, so we'll get some imperfection in the middle, right? So I have these defects that cause trouble. And usually when we do, I would say, non-sensitive measurements, it doesn't matter, right? I mean, we just kind of have billions of photons, a couple of them are lost. That's totally fine. But when you kind of come to single photon manipulation, like a qubit, then it basically makes a mess, right? Basically, every defect that you have could create some sort of an absorption. And basically, when you look at the diagram like this, you will have these TLSs. So this is kind of your, I guess, the photon qubit dispersion, and then these are where things are absorbing. So then, I mean, in the qubit, you already have a cavity, and then there is this James Cummins formula. So going back to the material science, what I really love to have, this is how this thing started, was that I want to have a crystalline junction. How can I make it? Aluminum oxide that is the best just doesn't come close, right? Because I have to put aluminum oxide, which is an amorphous material. I mean, it can be crystalline, but I cannot get crystalline on top of aluminum.
Why do you want crystalline?
So I don't want the TLS to cause trouble, the two-level systems, right? And then on top of that, if it's crystalline, then I can stack them anywhere I want, right? And I will get to that example.
TLS are unavoidable if you're amorphous.
That's one hypothesis.
Okay.
That's the idea, right? So what we have been done in the past is basically, let's say, aluminum and indium arsenide, which basically created this really nice lattice matching. If you do another material, let's say niobium tie on indium arsenide, then the interface is going to be bad, right? Just because the material science is not true. This really becomes a problem when you have two different crystals that you want to put it on top of each other, right? For example, for boring superconductors, let's say aluminum, you have a FCC. For niobium, you have a BCC, right? And then on your semiconductor side, you have a zinc blende structure, right? So it's not very difficult to put one of these guys on top of that, as I showed you in aluminum indium arsenide, but it's very difficult to put this one on top of any of these two materials in a crystalline type. Right? It's somehow fundamental to the material problem that if I have material A and material B, if B goes on top of A, in most cases, the reverse is not correct, right? You can't get material A on top of material B, right? And there are very, very different reasons why. There are the polarity of interfaces, there's a symmetry of the interface. There are just some magical materials that this is possible, like aluminum arsenide, gallium arsenide, just happen to have the same zinc blend, and then the lattice also is very similar, right? Lattice parameters. So, but otherwise, it's very difficult, right? It's just like you have to go to amorphous, and that's kind of your best shot, basically, right? So we kind of cooked up a really hard problem. And when in the old days, when I would see the first 2D material talks that were looking at gallium arsenide, and now we're kind of going back and looking at 2D material. In 2D material, it's actually very easy to do any kind of a stacking you want, right? They can put A on B and then B on A on B, right? Because this kind of like interface is, really not ionic, covalently bonded like this. But if we can do this, if I can find a material A, B, then I can create various things. And if one of them is a superconductor, I can create this kind of Josephson junction arrays or bilayers or 3 layers, anything I want, right? So this is kind of the problem statement that I'm looking for a material that I can alternate it, and it's even better if it's superconducting or it has this kind of properties that I want. And if the material, the solution turned out, this is one solution, I don't know, there might be many, many solutions, right? One solution is don't change the material. Change the property, right? That seems like the cheapest way to go forward. And then you have to dope, I guess, right? To change the properties. Like, I mean, you could have like a gallium arsenide that is insulator. I dope it, it becomes a conductor. Then I don't dope it, it becomes an insulator. I make a capacitor that way, right? And if I can do that, then I can change the thickness and layers because it's homoepitaxy. The material is the same, lattice is the same, crystal is the same. I can do whatever I want. To go to superconductivity, I have to ask 2 questions. Is there a superconductor, I can make it a semiconductor by doping? Or a semiconductor, I'm sorry.
Even for the gallium arsenide, for being ignorant, you probably need some doping layers in between.
For gallium arsenide and aluminum arsenide, it's perfect. It's just magical. Like Now you just take the aluminum, you put the gallium, vice versa, perfect crystal. It doesn't care at all. But some other materials, you're right, there's a diffusion barrier, there's something to help it. But this gallium arsenide, aluminum arsenide is just a magical example. But there are very few examples that are magical. Almost all of them got Nobel Prize, right? Silicon dioxide, Van Kilitz, and tried to kind of do better HEMS. That led into integer. Gallium arsenide, aluminum arsenide led to electron-electron interaction. Aluminum oxide, Josephson effect, right? But there are not many. So,
but just to be sure, implicitly in this, when you say if we can change properties by doping, the doping has to not mess up the things which give you good stacking.
That's right. Exactly.
And how much magic is required? Maybe
exactly. Exactly. Okay. That's my point. Right? So,
or you use also interfacial strain to do that?
We don't want to do that. We don't want to do that. Yeah, at least at this point, we don't want to do that. So maybe giving the answer up front, if you can replace one of the atoms with the dopant that you want, technically, the alloying content is huge. It's like 10%. But if I can really deterministically switch this with something else that can give me electron or a hole, I am already, maybe I can enable a new physics. We don't know for sure. Right? I just get a lot of electrons or carriers. But that doesn't mean that it's the right thing, right? But yeah, the idea is substitution. So the other question is there a semiconductor I can make it a superconductor? And this is kind of the answer. We're going to look at germanium case. The other one is a little bit difficult, but there are synthetic versions of that. So going back to this group 4, we're looking for magic. People studied this very early on in 2010 on silicon.
Yes. Okay.
Yeah.
You just say why germanium and not silicon?
Oh, both are the same technically. Actually, as you will see toward the talk, there is a ton of say, calculation needed for electron-photon coupling, for bands, whether they are flat band or not. And it seems there is a subtle difference between silicon and germanium. There are valleys, different valleys. We don't know if they matter or not. But from the zero photon, they're the same. Yeah, so basically, if you can basically brute force make superconductivity on group 4 by a non-equilibrium doping. That was the story in 2010. So you basically melt silicon, you put, let's say, gallium or boron on it, and then as you kind of like recrystallize it, then the boron somehow goes inside, and then it gives you a superconductor. Various temperatures. If you look at with TM, everything kind of comes to the surface. You kind of see a trace that is scattered. This particular one, I guess, is gallium and germanium, about half a Kelvin superconductor, right? The theory, which I should tell you up front, this is what was suggested, was that you basically start from a semiconductor, bare bone, valence band, conduction band. You put dopant, you have these localized states. You put more, you create a band. If this is clean enough and it's done right, you can open something like a Mott gap. And if you do more, then you kind of get this superconductivity appearing at the highest doping. So we call this usually a hyperdope semiconductor, right? And the BCS DC is very similar. It has the usual ingredients. What kind of comes down at the end of the day is the electron-photon coupling and the density of the state. So if you're a flat band, this is where it gives you superconductivity. If you have some strong electron-photon coupling, that term has to basically be maximized in so many ways, right? So we want to kind of maximize this one. So this is the simple picture. Many people tried, we tried a few years ago, and it was kind of a failure or maybe a success, depending on how you look at it. So you can make it superconducting for sure. This is R versus temperature. And you see that basically the curve, the black one, shows us something that goes to 0, around 4 Kelvin, and then there is a BC. They are very reminiscent of disordered superconductivity in so many ways. Usually there is a band, and then there's another band, and then it kind of goes to a superconductor. You look at the TM image, it's a mess, right? You basically love to see a flat line here and with an oxide on top. So these are hillocks that basically, if you zoom in more, you should be able to see different patterns of a polycrystalline material inside there, right? So this is not what we want, right? Something superconducted. We did another experiment to actually see gallium is melting on top, and gallium is a superconductor itself. So we kind of got stuck a little bit of what is next, right? And
Which is the doping level that you have?
I'll show you. I'll show you. This is one of
Right
them.
there, right?
Yeah. So this is a ITC plus, I guess, is a TC plus dopant and something superconductor. So we just put this here. I'll fix this number into per cube later. But the state of the art at this when we did that experiment was that look, whether you don't have enough doping, that basically things are not superconducting, or you have too much disorder, you have too much that basically now you are destroying superconductivity. So if there is a superconductivity, you want it to be in the middle, you want a lot of electrons, and it should be electron-driven superconductivity, basically.
Sorry, I missed one. How are the dopants actually introduced?
Oh, in this case,
Yeah.
you just basically put boron. Boron is group 3. It creates a hole, right? And then you put a lot. But there is the boron, like you have a glass of water, you put sugar, it saturates at the density that is much less than what theoretically has been predicted for superconductivity. So for superconductivity, you want 10 to the 21 per centimeter cube above. If you do that, actually maybe it's the next slide. This is like theoretical solution. These are like bulk material. You try to measure gallium.
But really in the liquid phase.
Yeah.
That's where the disorder is
Yeah, yeah.
strong because it doesn't,
Yeah, we are not doing a crystalline job here, at least not in this work, right? So then these are kind of like the ultimate limit of solubility of gallium in this particular material. You see gallium in silicon, you really cannot go above 10 to the 19-ish, right? And boron in silicon is up here, these various things. So we kind of gave up at this point. We just said this is not possible, right? What we want, there's a theory by Cohen in 1957, I think, 67, that says you have to be 1021 above, and you get a TC of about half a Kelvin. We just can't reach there, right? Until this idea that Antonio basically suggested that, how do you do this, right? Maybe there's another way. And then another very smart postdoc, and he said, why not we try to grow this in a regime that basically in the lattice of germanium, we just replace one with a gallium. So that way, yeah, this bond is distorted a little bit, but gallium and germanium, actually the mass are very similar. Then we will have an extra hole per unit cell. So now if you calculate, you can easily reach these kind of densities, if you can basically do that. So with the MBE, and I'm not gonna bore you with the exact material science that went behind it, we decided to grow this. So basically this is the germanium substrate, we dope it. In silicon, the spacer is just trying to kind of interrupt the superconductivity. We create another layer that we think is a superconductor and we end it. So it's like a Josephson junction vertical, right? So we tried this. You kind of make a whole bar again out of this, and then you measure it. And this is R versus temperature, and then you see that something superconducts. This is the critical field measurement. This is the Hall. We can get densities out. And then for the first time, we saw a density that was really high. It was like 5e 10 to the 21 per centimeter cube, right? This is kind of impossibly hard, even if you won't look at CMOS and the conductors. These are just really high numbers, right? So we were very excited. Obviously, I showed you the shortcut. We grew like hundreds of samples that didn't work.
And I ask one
Yes.
question. Maybe you already checked.
Yeah.
Are you getting to the doping level in which sigma bonds of germanium play a role?
I will show you. I don't know for sure.
Because this will give you the huge densities.
Right. There is a limit we cannot go beyond, and I think that limit is related, and I have that number in the next slide. I don't know what is the one-to-one relationship though, but it's easy to check. So we said, let's grow more of this type that we are thinking we are replacing. So we said, look, maybe we shouldn't put the silicon in the middle. Just grow something doped germanium. Just gallium, doped germanium, cap it, because germanium oxide dissolves in water. So and the humidity affects it. Superconducting. Yeah, the structure I told you, superconducting. Try to in-plane, out-of-plane magnetic field. Everything is reasonable. It's not exactly what you would see for a BCS. Like these are a little bit higher out of plane field, in plane critical field, but very reasonable. And then we basically said, what are the parameters here, right? If I plot TC versus this, how high can I get? And the highest we have ever gotten, assuming error bars, right? These are the 10 to the 22, I think we are very comfortable. 10 to the 23, I'm not sure. Like there's only one data point. And these graphs are such a low resistance that now you have to count for everything. But 10 to the 22, yeah, we have to put that number in, and maybe it's here. But if you go with 1 out of 8, that line is around here. We change the substrate temperature, try to kind of get the stability of all of these single layer, double layer, triple layer, everything superconducting. So we were happy. So we achieved a very high density. Now the question is it clean, right? Or was it a mess like the other one I showed you, right? So this is a cross-sectional TM of this double layer. You already see that it actually looks pretty clean. But you spend more money, you talk to your best friend who's a TM person, aberration corrected. Now you can look at this. So basically, this is the substrate. This is the doped gallium in germanium, which almost look identical to this lattice. And then this is where we switch to silicon, which follows the same pattern actually, because it's also the same diamond structure. And then we dope gallium again, and you almost can't say, except the small variation of the intensity, where is actually the junction, right? And the surface, as you can see from the zoom out, is just quite free, right? So for the first time now, we think we have a crystalline Josephson junction, right? Because this is crystalline, that is crystalline. It has a TC, which is actually probably more exciting than the junction. That what is the nature of the superconductivity here, right? Because we're just doping it at the very high level. Is it like electron-electron? Is it, there's a band that kind of comes in? And this is where I was saying that I threw away this point and I just draw a line here. And I think this is kind of unattainable. And that's why I don't know exactly, probably the fields are too strong and we can probably calculate this. But this is kind of in contrast to everything else that had been done before that basically could not make the barrier of the 10 to the 20. And for the first time now we can get few Kelvin TC at the level of with the normal electrons and disorder, right? So we are very excited about this. But obviously, the moment you find this, everybody says, "Oh, are you sure it is the right thing?" And so we actually worked with the University of Queensland in Australia to do a lot of kind of a structural analysis, right? So we basically did very fine-tuned synchrotron grade XRD to basically see sort of these fringe patterns. We are only growing 5 to 10 nanometers, so you really need a high intensity beam, and it basically matches exactly the thickness that we grew. Very well-defined, abrupt, which also was confirmed with TM separately. We then started thinking about this maybe from Raman type experiment. Can we sort of get any insight from electron-photon coupling? So we actually put a germanium substrate, and then we basically look at, this is the GVAX, and you kind of see that there is a peak for germanium here, and then when you dope it, there's a small distortion, but it's not like a massive number. So at least, so basically, this is consistent later, as I will show you with DFT, of just the substitution. This is where, again, this is not my expertise, but our friends over there, basically, they did this, the X-ray measurements, and basically what they find is that this is consistent with the DFT calculation that basically one atom is substituted, and there is no final structure that we could observe. And basically the final theory experiment conclusion is that, yeah, we managed to actually successfully substitute one gallium with the germanium in the germanium lattice. And with that, the fit and everything kind of consistent with this picture. So that's kind of the overall thing. So going now, asking ourselves, which I guess we really still need help, is that what is this superconducting? Right? What is kind of the underlying structure? And that's kind of tough. So we did sort of see. Yes.
You do have a limitation of the thickness of the.
No.
You can
choose grow as thick as you want.
Maybe I missed. Did you look at the either critical current or conductance to the junction?
We haven't
You have
done
this clean
much.
silicon, like maybe it's too thick.
We haven't done much junction, but we have been really sort of look at the nature of superconductivity itself.
No, I
Because
understand.
once you make a junction, now you have the bottom contact and the top contact. Those measurements are coming up, but we basically look at the DFT calculation because whatever it is, there is a germanium calculation and then there is a dope germanium calculation. There is something that is different. So if you look at this diagram, the red is when it is doped, the gray is when it's not doped. So on the valence band, there is not much going on the gamma point when there is this shift, except at the R point, right? Where the red and the gray kind of change quite a bit, right? So we thought maybe, and still it's a hypothesis, that basically at R point, maybe we are getting something like a flat band, right? And this flat band creates some pocket of superconductivity that proximatizes the main band, and then the whole thing becomes a superconductor. That's one idea, right? We are not sure, but then theoretically, if you also do calculation of phonon density of a state, it seems that there is a big difference, or measurable difference, between when you have pure germanium versus you have gallium germanium. So if that's true, that basically means electron phonon is also already modified due to this strain and then kind of distortion of the mass. Which one is true? We don't know. We actually do not see this in the type of experiment that would target electron phonon distortion. So we are still kind of staying with the first one, that is flat band. But it's also kind of hard to believe that, I guess, the small pocket, because this is 1 MeV, also proximatizes a lot of electrons here, right? But somehow maybe it is possible. Eugene can help me with this. So that was a small discovery that we had. And I want to now give you 2 teasers of where things are going and then kind of like how things come together. So if I now am able to make these Josephson junctions because I have a superconductor, I can react something in the middle and make another one. If I make a small dot between the two, I can actually trap an Andre bound state inside this object, right? And that happens just because I have a normal superconductor. I get these reflections, and then I have a field band and an empty band. For all purposes, this is like a spin. It's a 2-level system, right? I can excite from this side to that side. In principle, I can make many of these now because we are growing wafer scale, and I can basically put these pixels, and each pixel has a superconductor at the bottom and a superconductor on top, which basically traps exactly a 2-level system. We can call it Andre bound state, right? And then with the case in the middle, I can try to tune sort of the talking between these 2 things, right? So now we are actually back to this original description of the optical lattices in now kind of condensed matter system. So with a lot of nanofab effort, people have made the Andre bound state molecule, which basically is only 2 of those pixels connected together with a superconductor. And now we can, in principle, look at systems that have many, many of these pixels and then decide which ones want to talk to each other or not. So basically go to Andre bound state lattices instead of the molecules, right? So this, I think, is super exciting. I mean, the fact that what is the nature of superconductivity, that by itself is really cool. But now that for the first time, we have something that you can have basically this stacking of various materials with the thicknesses that you like, then there's a whole zoo of options available here. So we haven't really gone further on this. We are still characterizing Josephson junction. But on this type of synthetic material that basically would have, I would say, new directions, at least for us in superconductivity and proximity effect, I want to show you one more example before I end my talk. And that's also sort of a surprise, work in progress, is not published, is that going back to this indium arsenide aluminum Josephson junction, which is basically the same thing that I have, if these 2 are superconductor, this is an indium arsenide, I have an Andre bound state here, right? I have an Andre bound state here, I have an Andre bound state here. And keep looking at our colleague who do 2D material, and everything is hexagonal. So we can create this, aluminum, aluminum, aluminum with basically 3 junctions in the middle that are kind of my weak points, right? Working with Yuval Oreg, you can actually write a Hamiltonian that basically has the effective coupling of this. And remember, in superconductivity, the phase is special, so I can actually make the phase wind in one of the cells. And better than that, I can actually kind of create kind of a carpet of this hexagon, exactly like graphene. I can carpet it and basically change the way that these couplings are happening in my carpet. In this particular case, I have a T, which is a strong coupling, and a T prime, which is a weak coupling, just because the junctions are separated from each other a little bit further, right? So I have basically in my Hamiltonian, I have a T over T prime that actually gives me a phase space for how I can go to topology. So for this particular case, at least argues that if we kind of put the right number of these fluxes inside and they phase wind the way we want it, then you can actually get basically a kind of a Majorana that is chiral and goes around and basically in its phase transition, right? So I'm going to call the number of these fluxes per the whole unit F as filling factor. And we're going to try to tune some of these. Some of these trivial experiments have been done way back in the 90s. And basically, you just make this, crosses. And by putting a flux out of plane, you kind of see a filling factor of 1/2, 1/5, 2/5. Yes.
So this is like actual magnetic flux.
This is actual magnetic flux. So I just turn on the magnetic field.
So there is spin orbit coupling plus magnetic flux that you control.
Exactly. And for the filling factor, the only thing that matters is out of plane, but I can also put in plane. And I'm going to do it. Right? In all these experiments, they just put something out of plane. Right? So just tune it and then something appears. And it turns out some filling factors are very stable, right? The 2/3 shows a very strong dip, while, for example, 3/4 doesn't. And in the old days, at least it was vortex motion and the competition between vortices and all that, right? This thing has been now revived in 2DEX, and then some of these filling factors, I guess there are better data out there. But I'm just going to go straight to our experiment. So there is a hope for topology, but I think the synthetic part is even better.
Is this in the classical domain? The junctions are big enough that there's no quantum tunneling?
Great. No, this is in the quantum limit.
Oh, it is in the quantum.
So in the classical limit, in so many ways, this junction, let's call it the dog bone, right? They are so big that basically this doesn't know about the other one, this doesn't know about the other one. But if I make it small enough at the order of a coherence length of the junction, now these guys know about each other and kind of overlap, and then now you can have a macroscopic phase, right? So the hope is to make it small. So that's where the nanofab and everything comes in, right? And the idea is that if this T prime divided by T, right, if I can tune this, right, now I can basically go to a regime that I can have basically a topological feature based on the prediction of Oreg. So we basically get motivated by the theory. We are not exactly sure what we're going to see, but we were brave enough to go and just basically make these devices. So this blue is the aluminum, right? And these are the dog bones we were just pointing there. And then if you look, the whole thing is less than 500 nanometer, right? So basically, each hexagon fits in a 500 nanometer square. So I have 1, 2, 3, 4, 5, 6 Josephson junctions. So these are kind of my big junction, small junction, big junction, and small junction. And I guess this is kind of clarifies it. The big ones are 100 nanometer, and the small ones are 60. You actually can SEM them after the device and kind of exactly find the variations of these junctions. And they are very Gaussian and well separated, from both sides, right? So I will just show you one experiment out of the experiments we have done to show you this is interesting. And hopefully in the coming months and years, I'll tell you a better story. So this is measuring a supercurrent versus the filling factor. Filling factor was the field I was trying to put in flux, right? So obviously at 0, I see supercurrent. Yellow means supercurrent, right? This is the 0 resistance state. And as it goes, it may have some features, right? So this is filling 1, this is filling 2. These are the fractions. Interesting, right? So I'm going to see this is the out of plane field. and I'm going to apply an in-plane field to my device, right? So when I apply an in-plane field to my device at 150 millitesla, and I rotate the angle, right? So I'm basically sitting and I would rotate it, right? The lattice is a hexagonal lattice. So you would have thought maybe there is going to be a 6-fold symmetry, 3-fold symmetry in the device. There is none. I mean, the resolution here is bad, but it's a 2-fold symmetry of the oscillation of this, right? So we said, okay, if I apply 150 millitesla in the plane, and I look at the filling factors again. So basically at 0 in plane field, I see 1, 2, all of that. Now I put 150 millitesla, and I don't see 1 at all. 1 is gone. 1 is not a good number anymore, which was supposed to be actually one of the strongest phases that you can destabilize, right? So we put a little bit of an in-plane field. 1 is completely gone, right? And then you can ask, well, wait, what happened? Why 150 milliliters? Show me the whole graph, right? So this is in-plane field at 0, filling factor 1. You're just sitting at 1. There is a supercurrent at 150 millitesla is gone. I go after that, it comes back, right? So I know here my symmetry was 2-fold, right? What about this? What is it here? And the only difference, again, remember, it's an in-plane field. So when we go at 220 millitesla, where it's actually sitting in the after the reopening of whatever this is, now you kind of see a 6-fold symmetry oscillation of supercurrent with the angle, and you can actually line it up with the junctions. So it's a pretty big question for us that first, why should you have a closing and reopening? And why in that closing and reopening, the symmetry of the data is changing? Is there a phase transition, or is this something trivial, which is very strange? So following our work, this is a new device we are cooling down. So this is, let me just go back maybe even fast. So this is the array, the dog-bone array. Now I want to gate it. I want to know T over T prime, and I want to be able to tunnel at the edge to say if there's a chiral Majorana. Deposit a lot of gates. So these are the quantum point contacts that are going to tunnel into the edge to see if there is any chiral. I need 6 of them because I can measure Doppler effect, if there is something chiral or not. And then for the junctions and T over T prime, you basically gate this versus that, and then you can actually show what is going on. So this is also to be super interesting because now with this synthetic way, you have control over the whole system. You can actually measure the variations in every aspect, right? And we are already seeing super, symmetry changing behavior within plane field, which actually nobody else has seen anything within plane field, right? With a filling factor, you can argue a vortex interaction, but within plane field, I guess it could be related to a spin orbit or something, right? And then you can kind of bring up the topology. But in the case that I showed you, I can only measure supercurrent. If you can do this tunnel spectroscopy at the edge, it could be that we can measure something on the zero bias and other things. Anyway, so I hope I didn't confuse you. I made a case that I think now with some magical material science, we can substitute gallium in germanium, and it does superconduct, and it looks healthy, and it's crystalline. It's good for a lot of things, including Josephson junctions, but also kind of what is really superconducting and whether we can understand that. I'm sure there are many experiments one can come up with, including SDM and others. The other one is kind of these synthetic things that we can create now that you can have these vertical junctions, but also, I would say, planar old-style junctions that you can create various physics. Some of them may be very simple in terms of two-level system. Some of them maybe, a spin orbit is already built in and maybe topologies involved. Thank you so much.
We have a few minutes for questions, so. Mohammed?
So going back to the Andrea found state, you said that it's a two-level system. Does it depend how long this? If I think of it, when I tunnel an electron, the current that is going.
So right now,
Current is coming from the left to right during the ping pong.
So if you narrow it down, there will be a time that there is only a single mode that carries current, right? In terms of the geometry, imagine you have a QPC on top of your junction, and you kind of keep going down until the last mode comes up, right? So obviously, if you're in short ballistic, it's a lot better. And because this is vertical, you can make it as narrow as you want. The rest is the geometry of this, right? How many modes I can launch.
Long or short?
Depends. Do you want a spin orbit? Do you want it long? Basically, probe the spin orbit in the material. If you just want it to be can have Andrei spin qubit-ish two-level system, or you can have just Andrei two-level system. So Andrei two-level system doesn't need to be long. It could be just short. But if you create a long, then basically, if the lambda SO is this big, it has to be larger than that, so you can probe this spin orbit. Then you basically resolve the spin. If you apply field, you can actually lift everything. But the cool part, I think, is to just make a hexagonal lattice of all those and then let them interact with each other. Right? That would be the fun part.
But it was difficult to analyze numbers. We already know the answer. So in plane field which you apply, right, it gives you Zeeman's shift Andreev states.
So
how does it compare to the gap?
So with the G factor of 10, the gap of aluminum, which is 200 microvolt, is 600 millitesla G mu. So 150 is a quarter of the gap. Assuming the gap is not moving, which at some point it will close the magnetic field.
Somehow, like, I guess with frustration, right, your gap gets smaller. So could this be kind of opening and closing with the fact that some of your Andreev states actually cross zero and you end up with...
That would be great, actually, because yeah, we have no picture right now, but if that's happening, then the next question is, was a spin orbit involved? And if you have a spin orbit involved and Andreev states went to zero, you get really close to Majorana picture. Because the whole point of this proposal, at least with Yuval, maybe you know already, is that because you have out of plane symmetry breaking, then you don't need a huge in-plane field. Because that was the idea, that you're basically making a synthetic quantum Hall around zero field. That would be cool. That would be really cool. But we need better forms.
Any last questions? If not, then let's thank Yuval again. And